Alright, so we are going to wrap up chapter 7. Only takes me about a half an hour, so you will have some time to work. I still have like 81 of you that haven't started 7S, which sucks, but I guess that's your choice. So, as soon as this comes up, we'll get started. Alright, so it is 1:12 today, right? And just so you know that when I walk out that door at 6 p.m. tonight, this quarter's over. Okay? So just kind of keep that in the back of your mind. If you owe me a homework, or not a homework, if you owe me a lab or a test, it's today or it's never. So, alrighty, so it is 1:12 today. This is Chem 11:10, chapter 7 review, and this is second period.
What work that goes up all the way into the second quarter?
Say what?
So what's going to be the last thing in the second
The test for chapter 6. Like if you've done 7, all those scores are there, and they won't count against you or whatever. But everything from 6 before is on second quarter's grade. Okay. So yeah. Alrighty. So here is my 3x5. That is the front of it. And this is the back of it. And that is the test. Okay. We're going to walk through most of this, answer some questions, then give you some time to wrap things up. Yeah. Alrighty. So, first thing I have written down is you've got to know conversions. Okay, you got to be able to convert. We're talking from MM, HG, ATMs, PSI, yada, yada, yada. You got to be able to convert them. I've given you those values. We've already done them. That should be enough of that. Okay? You need to know all gas laws. All gas laws. Now, you don't need to know them by name. Like, they're not going to say, hey, what is Guy-Lussac's gas law? They're not. But you do need to know how to use them. Okay? With that being said, you do need to know what value. Anybody remember what value I told you to remember? When it came to gas laws? The universal gas constant, which was what? No, what was it? R, right? Told you remember what R. What is it? 0.0821. Got to have units. Liters times atmospheres divided by moles times Kelvin. You need to know them. Okay? You need to know that. All the other values, like all those S's, H of F's, H of V's, they give you everything you need in the problem. Every time. Okay? So you won't need to know any of those. You guys know what I'm talking about. We spent one day on heating curves, right? I think that's all we taught that day, wasn't it? Yeah, and all those 5, you had the 3 S's for S is solid, S is liquid, S is gas, right? Then you had the 2 H's. They give them to you on every problem. They're there. So you don't got to worry about that. Okay? You do need to know this, that 1 mole is equal to 22.4 liters. Now, what is the caveat of that? That is only if it's at what? At, what did I call it? I heard it. At STP, which stands for standard temperature and pressure, which was 1 atm and 0 degrees Celsius, right? So make sure you do remember that. Now, they do ask you a question that looks something like this. This is not the question, but it is similar to this. And it says, what volume would 4.27 times 10 to the 25th molecules of N2 occupy at STP. Okay? So I want to know what volume would that many molecules occupy at STP. Now what's I don't know, what's different about that question? Yeah, it has molecules instead of moles, but I'm pretty sure we should have the technology to go from molecules to moles, right? So I would start out with my 4.27 times 10 to the 25th molecules, right? Of N2. Where am I going to go first? To moles. Now, how do I go from molecules to moles? I'm going to go 1 mole in the numerator, so I got 1 mole of N2 in the numerator, and I've got just times 10 to the 23rd molecules of N2, right? Molecules are going to go away. Now I'm in moles, and then I'm going to times that by what? 22.4 liters of N2 for every 1 mole of N2, right? Moles of N2 are gone, and I do that math, and I'm going to get what out? 1,590 liters of N2, and that is in sig figs. Anybody back Fisher up? Yeah? Okay. Or, what else could I have written there and been okay? What's the matter?
I was trying that 1,590.
Yeah. Is that what you got?
I
You didn't do it.
not yet.
Freaking 10. Have I mentioned that we should all have calculators out and bring them to this class? At any point in the past, I don't know, how long we've been in this class? 5 months? 4 months? Have I ever said that? Yeah, I'm pretty sure I have. I know a guy. I even have my own basket for you to borrow one. You're welcome. She's oblivious that I'm talking to you. Okay? Now, I still don't have anybody with my or statement here. Yo.
Would it be the 15.9 times the...
He's on the right track, but what's wrong with that? Does anybody know? Men and all? Yeah, I can't have 2 digits out in front. I can only have 1. So it would actually be 1.59 times 10 to the 3rd liters of N2. Does that make sense, Brian? You only have 1 digit out here. Okay? Alrighty. Then we got to go through intermolecular forces. Okay, we talked about this last time. What are they? What are the weakest? Blend and dispersion, right? Then I had dipole. What did I look for? Determine whether or not dipole is happening. Lone pairs. Now, typically, where are those lone pairs? Does anybody know? They often are on the oxygen. Do they have to be on the oxygen? No, so make sure if you have to, draw them in there, right? So yeah, make sure you remember that. And then the other one was hydrogen bonding. And what were the key here? Dipole was lone pairs, right? Hydrogen bonding was H2 and F, O, and it's easy. Think ET. Nobody's ever seen ET? What does ET always say? ET, are you kidding me? Nobody here saw ET? Mendenhall, quit being a cool guy. Okay, it was always ET phone home. Phone. Get it? F-O-N. ET phone home. Yeah. Just, I don't know, something I thought of. Okay. Now, on the homework, and I realize there's 81 of you that haven't done it. Yeah, I'm looking at all of you, except probably you. Have you done 7S? You started it? Okay. Well, 81 of you haven't even started it yet. Shame on you. Your fault, not mine. Okay. There's a blank box on 7S. There's a problem that is missing. Right? Do you know the one I'm talking about?
Huh?
Do you know the one I'm talking about?
Yeah, I missed it.
Okay. Well, I'm gonna answer it for you. Okay. So, the blank box. So 7S, blank box. I don't know what's in it, because even on mine it's missing. Okay? But I do know that it is all three. It has all three kinds of bonds. Which tells me what about it? It's going to have the most, or it's going to require the most energy, right? Which means it's going to have the highest what? Boiling point, right? It's going to have the strongest intermolecular forces. Okay? Why is Kent's late today?
I have to talk to my counselor.
Oh.
And you can't call me that anymore because I don't work there anymore. So you have to call me a different nickname.
What's that about?
I quit because I hated it.
But my wife likes Kent's. And I could see you when I went in there. And I'm going to be honest, I'll probably still use that nickname.
Okay.
Some things live with you, okay? I don't know what it is. I have a group of friends from high school. We get together once a summer and go golfing. Hell or high water. Same group every year, right? And we still use the same nicknames from 35 years ago. So, it just...
Just accept it.
See, you're learning now. You just accept it, because I don't especially like mine, but I still get called it. It was, I'm not even going to tell you. Okay? Now, so, here are a couple of questions they're going to ask you. Okay, they will give you one just like that question on 7S that Heslop missed. Okay? And they will say, which one has the lowest boiling point. Well, the one with the lowest boiling point is going to be the one with the weakest bonds, and the weakest bonds are the London dispersion. Then it would ask you something like that question which says which one has the highest boiling point, and that's going to be the one with the strongest bonds, which are hydrogen bonds. But more importantly, if it's got hydrogen bonding, it typically has all three, right? We saw that day we did that problem. Okay, it's just something to keep in the back of your mind. And I actually wrote it right up there on the board, but I realized that kids that are at home won't be able to see that. So 7S, that's an S. 7S, blank box, has all three. Okay? Alrighty, so... okay. Something we need to talk about really quick, and that is sublimation. Okay, sublimation. Anybody know what that is? Solid to a gas, right? Solid to a gas. What kind of process is that? Does anybody know? As far as the energy goes, what does that have to do? We talked about this a little bit the other day with my cup of ice and Mountain Dew. Okay, sublimation is similar to what? It does have to do with heat. That's what I'm asking. Okay, Shiv's on the right track. He just doesn't know which one the answer is. XO? It gives off heat when it goes from a solid to a gas?
No, it's endo.
Yeah, now you see what I'm saying. This has to be endothermic. It has to absorb energy. Just like if you spill on yourself, right? Okay, like when I was a kid, I had this one pair of jeans that I just really liked, right? Just really liked. And I remember one day I had an outfit I wanted to wear. Must have been a Friday, right? And I realized I get up Friday morning and my pants are in the washer. Okay, well, what did I do? You think I woke up early enough for that, Brian? The answer to that's a hard no. I put them on wet, right? Hey, I had to look good, right? Now, but by second period they were what? Dry. What happened? All the water evaporated. Why? Yeah, 'cause my body heat's pretty warm, right? I'm 98.6 degrees. Well, evaporation is just like sublimation because it's going from high order to low order, right? So that's an endothermic process. What's the opposite of this? Deposition. Deposition is exothermic. It's releasing energy, right? What did we talk about? We didn't talk about deposition. We talked about condensation. Same thing. Condensation is exothermic, right? So things like that, okay? Alrighty, so that is that. That is that. Oh, okay, with this, we have to talk about, well, somebody remember the term vapor pressure in a minute, okay? So, we need to talk about, yeah, I can't even tell who that is.
Still out. I'm taking my best.
Oh, okay. Q equations. Q equations. What are they? There's two of them. Q equals S times M times delta T, and the other one is Q is equal to or H of V. Now, how many S's were there for water? Well, how many S's are there for everything? 3, right? What you realize is that it will give you all 5 of these on every problem. Does anybody know why it does that? More likely than it's to what? No. To confuse you. Because if it gave you just H of F, I would know that I've got to use H of F. You know, if it's melting, right? But if it's boiling, I need to use H of V instead. So it's going to give you all 5 of them on every problem. And they're not always in calories. Sometimes it's in joules. But it doesn't matter. Because if the problem asks you for the answer in joules, the values they're going to give you are going to be in joules. If the problem asks you for calories, the values they give you are going to be in calories, so it really doesn't matter. If you know how to use those 2 equations that we spent an entire day on, I think that's all we did that day, wasn't it? You should be fine with those. There's like 4 of those on the test. Okay? Alrighty. So from there, you do need to know R. Did I already write that down? Yeah. I already did R. Okay. I'm teaching this in a little different order than my last class. Sorry. That's why I said someone had to remember what? Vapor pressure. Now, does anyone in here know what vapor pressure is? Nobody? Vapor pressure is the liquid pushing back against the atmosphere. Do you know what I mean when I say that? Anybody? Nobody? Okay, so when I have water, let's say I fill up a glass full of water. That water is fairly cold, right? Does it have a very high vapor pressure? Meaning, is the liquid turning into a gas very readily? No. How do I change that? I heat it up, right? So by heating it up, I change its vapor pressure. Now, every liquid has its own vapor pressure. So ladies, I don't know, guys, okay? Who in here knows what acetone is? I got one. That's it. Yeah, it's actually nail polish remover, right? So that's acetone. Now, I got 2 cups here. Over here I got water. Over here I got acetone. Which one has a higher vapor pressure? Anybody know?
Water.
Water does? So if I put these on the counter and I come back tomorrow, which one is still going to have liquid in it?
Water.
Water?
Yeah.
But you just told me water had a higher vapor pressure. So it's willingness to evaporate. Okay, if I put acetone in a cup and I come back tomorrow, guess what? It's gone. Because acetone has a high vapor pressure, which means there's a whole bunch of gas particles above it, because it's just saying, I'm out of here, I'm out of here, I'm out of here. So if acetone has that many gas particles, how many gas particles would water have? Not very many, right? Because it has a much lower vapor pressure. Now, what if I did the same thing and I put some vegetable oil out on the counter? And I wanted to compare those three. How many dots would it have above it? Maybe one, right? Because it has an extremely what? Low vapor pressure versus this one, which has a high vapor pressure, because it wants to turn into a what? Gas. Which is why if you don't put the lid back on it, you're going to come back and that sucker's going to be gone and you wasted all your freaking money. Right? It's like when your kid fills up the freaking lawnmower in the summer and doesn't put the lid back on the gas can. There's $7 of gas in the atmosphere. Yeah, that's happened to my house more than once, which is why I get a little pissed off about it. You know, it ain't that hard. Put the lid back on it. Right? No one's ever, like, in the summer, like, seen a gas can from afar and seen what it does to the light around it. You know, me and Jenkins, it looks all distorted. Well, what is that? That's the gas vapors distorting the light. That's why it looks all funky. It's really, really cool. One of the best GIFs, you know what a GIF is? Yeah, see how I'm thinking like a teenager. Y'all know what I'm talking about. Yeah, see? Yeah, I mentioned acetone, and so I got one girl, right? So the best GIF is a dummy that takes 2 5-gallon things of gas and dumps them all over what I would consider a mountain of shit to burn. Anybody seen this? They dump it on there and like forever. It takes them forever, right? Well, all that time they're dumping them, it's the heat of summer, all that gas is doing what? It's evaporating. And when gas burns, did you know that it's not the liquid gas that burns? It's actually the gas vapors that burn. He lit that, you would have thought a bomb went off, man. Kaboom! And it took that pile of garbage or whatever it was and just obliterated it. And it wasn't that it burned it, it just spread it out because of those vapors, right? Okay, so if I did that with acetone, it's going to burn just like that because of all these vapors. Okay? Alrighty, now, you do need to do some heating curve questions. Now, we're going to do an example of one because they don't approach them all the same. Okay? Let me explain. So, this is what I got. If I add 72.4 calories of energy to 3.15 grams of H2O at 27.0 degrees Celsius, okay, what would be the new temperature? Okay. Now, for starters, I need somebody to tell me what is different about this question than about all that stuff we did that one day.
Not going from temperature to temperature, we're just adding
Okay, so usually when we did it, we were finding Q, right? In this problem, I actually have Q. So what am I looking for? Now, ultimately, the question says I need the new temperature. But to find my new temperature, I've got to find my what? I heard it. My delta T, right? So, I'm going to go Q equals S times M times delta T, right? I have my Q now, so that is 72.4 calories, right? Equals S. Now, they'll give you this. I'm in calories, though, so I should know this, right? Wasn't that 1.0 calories per gram degrees Celsius, right? Times that by my M. What's my M? 3.15 grams, and then my delta T is actually what I'm looking for, right? Correct? So I'm basically going to divide both sides by, and really does the 1 matter? No, so basically by 3.15, by 3.15, and I'm going to get delta T equals, anybody have this? 22.98. And that would be 22.98 what? Degrees Celsius, right? Now, a really good question was asked in my last class. They're like, but Mr. Denton, that's colder than what I started at. I can't add heat and cool down, can I? Can I add heat and get colder? No. Oh, well, who is that? Is that you, Brian? Okay, answer that for us. That's just the change, and that's what's important. So what's the answer to this going to be? Actually, 27 plus that. So I'm going up, right? So I'm going to take 27.0 degrees Celsius. And I'm going to add to that 22.98 degrees Celsius, and I'm going to get what? 20 what? 49.98 degrees Celsius. Now, another little caveat here. This morning, I had a kid in here all flustered. Kind of, I would say a little upset. And these were his exact words. He goes, Mr. Denton, he goes, I've done this problem a couple of times, and I know my math is right. I know it is. Yet it keeps marking it wrong. And I looked at him and I'm like, you're a special kind of soul, aren't you? Because what is the one thing we have talked about when we were done with the problem every time for the last 2 or 3 months? Sig figs. He literally looked at me like he had just discovered girls. And I'm like, how did you not? And he goes, I don't know. He goes, I just didn't. I'm like, that's the first thing we've talked about, right? Now, this one poses a problem, doesn't it? It'd be 50? Okay, so exactly, I would have to go 50.0 because I got to have what? Got to have 3 sig figs, right? Well, does that 0 count?
Yes.
Yeah, because it's got a decimal in it and all zeros after a number count. So, something like that. And he immediately put in the right sig figs and got it right. And I'm like, man, only a boy would be upset like that. And not, I mean, because let's face it, you know, girls are a little more conscientious that way. For the most part. I mean, not all, but for the most part. So, well, obviously except Heslip. Okay? Alrighty, now, from there, we've got to address the most common question I've seen. Now, pay attention to this, okay? The book does a poor job of this. Poor job. Okay, now how many of you know the question I'm talking about? Nobody? I want to say this was a Learn Smart question. It asked you about like calcium carbonate and some other things. Now, there's 5 things they're going to talk about right here. There's 2 questions on the test. Okay? And the first thing they address is there's two main kinds of solids. There's what's known as a crystalline solid and an amorphous solid. Okay? Amorphous is like irregular things, right? Whereas crystalline is very highly ordered, like a diamond, versus like just some kind of rock. You know what I mean? Now, this is where it's really important. You have an ionic solid, you have a molecular solid, you have a network solid, you have a metallic solid. Now listen. In order to be an ionic solid, it has to be an ionic compound. Which means what? Metal to a non-metal. Or it could be a metal to a what? Something, I heard it. A polyatomic ion. Like, I think the example on the homework is calcium carbonate. Nobody's done that problem. I've gotten like 7 emails about that question alone. Okay, so that's an ionic. These two are the hardest. A molecular versus a network. Okay, this is page 252. Write it down. There are 2 questions on the test from this page. Kid in my last class gave me a creepy wink. He actually did it to me. Literally. I'm like, he's right! This many are right there, if you're catching my drift.
Yeah.
I don't know if you guys are picking up what I'm putting down or not, but yeah? We sure? Because I'm like, I don't know if I could be any more obvious without just coming right out and saying, hey. Good? All right, now, the next thing is some artwork questions. And I'm tired of us missing the artwork questions. So what I've done is I've tried to find a couple really good examples. And this is what I've got. Now look. When I look at the artwork here, okay? Now, that was not intentional whatsoever. Not. So we're going to do this. Okay? I was going to upload this video. I still might. What? Obviously you don't know me very well. Yeah, I grew up on a 300-acre horse ranch, and my grandfather taught me that anything that was said towards a cow or a chicken or a dog or a turkey especially was okay. So, you know. Now, look. This obviously has extremely high what? Organization, right? It's ordered. This one, he's using the exact same stuff. It's just no longer ordered. This is a solid. That is a liquid. Why is it not a gas? They're still touching. Do you see what I'm saying? Now, if I compare that to this, okay, this is still a liquid. This is now a gas. What step is that? Okay, what would we use there? Let's start with the V. Vaporization, right? Make sure we can see how they're trying to explain that. Okay, I'm tired of us missing that kind of question. Same thing can be said here, and they've just done it a different way. Okay, if I look at that, you know, that's pretty obviously, that sucker's a solid. That sucker is a liquid. Make sure we can decipher what those pictures are trying to say. Ordered, not ordered. If I wanted to make that a gas, I'm simply going to put some what there? Some space in between each one of those spheres. Is that, we all getting what I'm getting at there? Alrighty, now, like here's a really good one, like right here. Obviously a solid, a liquid, a gas, that type of thing. Okay? Now, who can remember why these parts were flat? It's the phase change. There's no what going on there. No temperature change, right? A couple of things to remember there. Alrighty, so let me... Just want to make sure I cover everything. Alright, now one of the things, do not be surprised when they do this. Anybody know what S would be in joules? What is the S we used? 1 calorie per gram degree Celsius, right? Does anybody know what that would be if they wanted it in joules? What?
4.184.
Yeah, just 4.18 joules per gram degree Celsius. So don't be shocked when they put stuff into joules instead of calories. Just know that the answer they're going to want you to find is going to be in joules, so it actually makes the math easier than harder. But you're going to look at it and go, wait a minute. But the answer's in joules, so it's not any different. They just used a different unit to try to confuse you, which it's going to happen, okay? And then I wrote this down. I wrote stronger. If I have stronger intermolecular forces, do I have a low or a high vapor pressure?
Low.
Low or high?
Low, because you have a higher boiling point.
Right, lower because I have a higher boiling point. So this is going to be a low vapor pressure. Low vapor pressure. Okay? Now, when I leave school today, and I will leave today at 6 p.m. 1:45 is over. Do we all understand that? I will take whatever your percentage on Canvas is, and I will correspond that to a grade on my student. After this quarter, I will never enter anything again on my student other than your final grade. There's a whole FERPA thing going on right now, and like next year I had to completely change my disclosure. Legally, technically, I am not supposed to share information with your parents, which I find completely baffling, but that's what the law states. Yeah, I was shocked.
What kind of information?
Any of it. Any grade information.
Really?
Yep. Yep. Yeah, it was. They sent out like a 2-page addendum that says you must put this on your disclosure. You must explain this to your students on day 1. You must email this home to parents. Yeah, I'm like, damn. Yeah, I don't know. So it's one of those things that if your parents want to know and you want to show them your Canvas grade, that's between you and your parents. I'm assuming you live in their house. I mean, that's what it would have been at my house, but I'm just saying, I don't. I was shocked. And this has only been like 3 weeks ago. They sent this out and said, hey, this is the way it is because it's the law. So go figure. So starting, like I used to, and that's why I stopped. If you notice, I stopped updating the portal at all. That is why they sent those emails out. So, yeah. So I had a girl that's had an F all quarter because she missed the first test, right? And I'm like, well, I can't. I can't. So if your parents are, bitching and boning about it, just get on Canvas and show them that score because that's one that matters. But I can't.
So that grade won't be updated?
What
on the
grade?
portal?
Tonight after 6 it will.
Oh, okay.
Yeah, just your final grade will be changed. That is it. And that's what I'll do the rest of the year.
Okay.
Then my student will be blank all quarter long. I will go and submit a grade the last day of the quarter. It's like today when I leave at 6, this quarter's over. I probably won't submit them until tomorrow morning. But, that's just the way it's going to be. Because I like my job and that's the law. So, I like doing what I do. Okay? Now, I do want to do one last problem before I cut you loose to work on this, and that is this one. Alrighty, so if I gave you these two compounds, Wish I had a stamp or something. And it really doesn't matter. I'm actually trying to prove a point here, but it's irrelevant. Okay. Now, here you go. So, if I were to say which one of these has a lower, or is more likely to, we don't know for sure, but is more likely to have a lower boiling point, thus it ultimately has a higher what? Vapor pressure. Which one of those would it be? The bigger one?
The big C, the C in
This one?
Yeah.
Why?
Because there's no.
Yeah, because it has the weakest intermolecular forces, right? This top one is going to do what? How is it going to intermolecular force?
It has all of them.
It has all of them. It's going to hydrogen bond because it had an H bond to an O, right? It's also going to dipole because they're not there. I didn't draw them, but I know that they're there, right? And if you go back to what I said about London dispersion, what did I say? All of them have it, so it's also going to have London dispersion. This one is going to only have London dispersion. Even though it's got a lot more carbons, and it's a lot bigger, its bonds are still the weakest. So this one would have a lower boiling point. This one would have a higher boiling point. The higher the boiling point, though, lower the vapor pressure. The lower the boiling point, though, higher the vapor pressure. Does that make sense? So this one would have a higher BP. Lower BP. This would have a lower BP and a higher VP. Does that make sense? Yo!
How do you I'm just confused on how you find the London dispersion.
Oh! If you go back to my notes, I believe, I'm trying to remember what I wrote out to the sides. Let me remember what I wrote. But I wrote like something specific. Oh, like I wrote London dispersion, then after the rod I wrote something. Say it again. All molecules, is that all I wrote?
Yeah.
Yeah, so all molecules, no matter what it is in this sense, exhibit London dispersion. Okay? And then it's an elimination after that. Then it's lone pairs. Does that have lone pairs? It's got lone pairs, then it's probably going to be dipole-dipole, right? Then do I have an H bonded to an F over an N, phone home, right? Then it's going to be hydrogen bonding. And if you go back to that question I talked about on the homework, it has all three, which means it has the highest boiling point. But only like 2 of you have done that, so you know you're the only 2 that know what I'm talking about. The rest are going to get there. Dude, do you think I like to be that guy?
I promise not.
If you noticed, I'm always, because my goatee catches it, and as I talk, mine always moves down, so I'm always moving it up. No, I get you, it sucks, but again, I like to teach, and they keep telling us, oh, we got to police it better. I'm like, oh, whatever. So let me check my notes really quick. That's it. Alrighty. One last peek at my 3x5. I'm actually gonna do this. That's the front. There were those artworks. That's the front of my 3x5. Here is the back of my 3x5. I think that's everything. Okay. If you need to look at that closer, go home and push pause, because this will be up in a couple hours. Okay. All right, time is yours. Let's use it wisely. Remember, 6 o'clock tonight is it. You owe me some. I need